Welcome back. This is part B of concepts of section 11.6, which is absolute convergence and ratio and root test. So earlier we saw the definition of conditionally convergent series. A series which is convergent but not absolutely convergent is defined to be conditionally convergent. So we saw that as the alternating harmonic series is an example of a conditionally convergent one. Then if a series is absolutely convergent, then it is convergent. That was theorem 3. Now let's see an example. Determine whether the series sigma cosine of n over n square, which is expanded as cosine 1 over 1 square plus cosine 2 over 2 square plus cosine 3 over 3 square is convergent or not. We are going to test this series. So what is our first observation about this series? You cannot say that this is alternatively positive and negative because cosine 1, some of the terms are positive, some of the terms are negative. It's a mixed series. It's not alternating series. It's not all positive either. So it is, this series has both positive and negative terms. So it makes sense to discuss about its absolute convergence. In case it was absolutely convergent, then we can conclude that it is convergent by this theorem that we stated earlier. If a series is absolutely convergent, then it is convergent. So let's discuss about its absolute convergence. Is it absolutely convergent? So for that, we have to take absolute values of the given terms. Consider absolute an, is sigma, n varying from 1 through infinity, absolute cosine of n over n square. So n is always positive, so n square is positive too. So it's only absolute of cosine of n over n square. So let's use comparison test. So what do you know about cosine n? So cosine theta, absolute cosine theta, the maximum values are less than or equal to 1 for any value of theta. So absolute cosine n is going to be less than or equal to 1. So let's use comparison test. So sigma absolute an, which is equal to sigma n varying from 1 through infinity cosine n over n square. And here, absolute cosine of n over n square is less than or equal to 1 over n square. Why? Absolute cosine theta is less than or equal to 1. So absolute cosine n is less than or equal to 1. So now what do you know about this particular series, sigma 1 over n square? But 1 over n square, sigma, is a p series with p equal to 2. So it is convergent. Thus, by comparison test, can conclude sigma absolute cosine n over n square is convergent also. In other words, we are saying sigma absolute an is convergent. Proving that sigma an is absolutely convergent. Absolutely. And hence convergent. Absolute convergence implies convergence. And this is the conclusion of this problem. Okay, now let's see what we mean by ratio test and root test. If limit as n approaching infinity, absolute a sub n plus 1 over a sub n equal to L, and if that L is less than 1, then the series sigma an varying from 1 through infinity is absolutely convergent. And therefore convergent. 2. If limit is n approaching infinity, absolute of a sub n plus 1 over a sub n equal to L is more than 1, or limit is n approaching infinity of this ratio of the n plus absolute value of the n plus first term over the nth term equal to infinity, then the series sigma an is divergent. If limit is n approaching infinity a sub n plus 1 over a sub n equal to 1, then the ratio test is inconclusive. That is, no conclusion can be drawn about the convergence or divergence of sigma an. The ratio test. So let's see an example based on this. Test the series sigma n varying from 1 through infinity, negative 1 to the power n times n cube over 3 to the power n for absolute convergence. So we'll apply ratio test here. So always we assume without the sigma, in the given series, if you consider the expression without the sigma, that is the nth term of the given series. So we will consider an, which is negative 1 to the power n, n cube divided by 3 to the power n. Then we will consider a sub n plus 1, which is obtained by changing n to n plus 1 here. We will change the n to n plus 1. So we get negative 1 to the power n plus 1 times n plus 1 cube divided by 3 to the power n plus 1. So now we will apply the ratio test by taking the ratio of n plus first term over the nth term, and we will take the absolute value. It's negative 1 to the power n plus 1 times n plus 1 the whole cube divided by 3 to the power n plus 1. Then I'm dividing by an, which has got both the numerator and the denominator. Then I divide, it gets, we are going to multiply by the reciprocal. So it is 3 to the power n over negative 1 to the power n times n cube. So we'll simplify this. This is going to give us negative 1 to the power 1. Then it is 3 to the power n, 3 to the power n plus 1. That will give us 3. So if you reduce this, you're going to have -1 times -1 divided by 3, then n plus 1 the whole cube over n cube, which can be written as -1 divided by 3, n plus 1 over n to the power of 3, the whole cube. Now you take the absolute value of this ratio, so which is absolute value of -1 over 3 times n plus 1 over n, the whole cube, which need not even be inside the absolute sign, because n and n plus 1 all are positive. It can be taken outside the absolute sign as well. The absolute value of -1 is 1, so 1 over 3. Then we will write n plus 1 over n as n over n plus 1 over n. So it will become 1 plus 1 over n to the power of 3. Now you take the limit on both sides. Limit n approaching infinity. Limit n approaches infinity. And limit n approaches infinity. 1 over n will become 0 here. So it is just 1/3 times 1, or it is 1/3, which is a value L which is smaller than 1. So the ratio test tells us that if this ratio is equal to L less than 1, then the series is absolutely convergent. So by ratio test, we can conclude the series sigma n varying from 1 through infinity -1 to the power n times n cube over 3 to the power n is absolutely convergent. The question is asking us to test whether the series is absolutely convergent. It is absolutely convergent. Because it is absolutely convergent, you can even go one step further and say that it is convergent in this particular case. Test the convergence of the series sigma n to the power n over n factorial. So this is part C of concept video on 11.6, which is about absolute convergence, ratio, and root test. So sigma n varying from 1 through infinity n to the power n over factorial n. So anytime you see factorial n, the hint would be to go for the ratio test. If you see factorial n. So let's recap what this n factorial means. So 3 factorial stands for continued product up to 3. 5 factorial stands for continued product up to 5. So factorial n would mean 1, 2, 3, 4 continued product up to n. Also, in the process, we may be using another result here. So when you write 5 factorial, you can write this as 1, 2, 3, 4 continued product up to 5. You can also write continued product up to 4 times 5. But continued product up to 4 is 4 factorial times 5. So if you have to generalize this, you can write factorial n as n minus 1 factorial times n. We may be using this idea often in our problems. So let's start the ratio test. Start applying the ratio test. So a n is without the sigma sign here. So a n equal to n to the power n over factorial n. A n plus 1 is obtained by replacing n with n plus 1. So n plus 1 to the power n plus 1 over n plus 1 factorial. We will divide one by the other. A n plus 1 over a n. Here in this problem, we don't even have to apply the absolute sign because all terms are positive here. So the numerator is a n plus 1. Then you're going to divide by a n. So you're going to flip and multiply by the reciprocal, which is factorial n divided by n to the power n. If I group this, we will reduce this n factorial here. Then this n plus 1 factorial can be written as n factorial times n plus 1. The same technique that we mentioned earlier. The n factorial times n plus 1. So here, this factorial n get cancelled out. Factorial n get cancelled out. And here we have n plus 1 and numerator is n plus 1 to the power n plus 1 divided by n plus 1. And we have, along with that, we have 1 over n to the power n. So if I cross out one of them here, I'll get n plus 1 to the power n. So this becomes n plus 1 to the power n divided by n to the power n. This is n plus 1 divided by n to the power n. If I reduce it, it's n over n plus 1 over n to the power n. It's 1 plus 1 over n to the power n. Now if you take the limit n approaching infinity of a n plus 1 over a n. In this particular problem, whether you use absolute sign or not doesn't matter, which is limit as n approaching infinity of 1 plus 1 over n to the power n, and this is equal to e. This is equal to e. You might have done this value, this expression equal to e in your calculus 1 class. In case you forgot, you may want to try this problem. Take f of x equal to 1 plus 1 over x to the power x and use the logarithmic derivative and try to show that this value is equal to 1. So in your calculus 1 class, you would have done this kind of problem where you would have found out the limit of the function f of x, which is of the form 1 plus 1 over x to the power x. As this is of the form, base is a function and the exponent is a function as well, you will do ln on both sides. And then when you do ln on both sides, and then you would apply L'Hopital rule to find out the limit, use ln and L'Hopital rule, the logarithm and the L'Hopital rule. To find the limit. So you would find that ln of f of x would be equal to 1 as x is approaching infinity. That means that f of x would be, the limit of f of x would be equal to e. You can prove this from the techniques that you learned in calculus 1. So you would prove that the limit x approaching infinity of f of x, which is limit as x approaching infinity of 1 plus 1 over x to the power x, would be equal to e. That's exactly what we are using here. But e is a number between 2 and 3, so it is more than 1. Therefore, in this particular problem, by the conclusion is that by ratio test, the series sigma n to the power n over factorial n is divergent. Hope this video helps. We will be continuing with this material for root test. So that will be part C of the concept video of 11.6. So please watch part C for continuation.